Welcome back to another explainer. Today we're taking some of those abstract ideas you probably remember from math class, those little lines plotted out on a grid, and we're going to translate them directly into real-world, high-speed action. We are going to completely decode the secret language of motion. So imagine you're a detective, but instead of footprints or fingerprints, your only clues are just ink strokes on a piece of paper. Can you actually read the secret story of a moving object, whether that's a parked car, a speeding train, or even a rocket taking off, just by looking at the shape of a single line? Well, the answer is an absolute yes. Okay, let's dive right into this. Here is our roadmap for today. First, we'll cover the language of motion. Second, at rest and steady. Third, the curve of acceleration. Fourth, calculating your velocity. And finally, who is moving faster?
Okay, section 1, the language of motion.
Before we can track a thrilling, real-world journey, we kind of need to understand the visual map we're using to navigate, right? And that map is the position time graph. Just think of the horizontal axis running along the bottom as a clock ticking forward. That represents time. The vertical axis running up the side, that represents position, so literally where the object actually is in the physical world. By tracing a line across this grid, we are quite literally drawing a picture of an object's physical journey through time. Moving right along to section 2, at rest and steady. Let's set the scene. Picture a car sitting in a driveway. The engine is off. The trip hasn't even started yet. If an object is completely stationary, our map draws a completely flat, straight horizontal line that runs perfectly parallel to the time axis at the bottom. The clock just keeps ticking, seconds are passing by, but the position on the vertical axis, it refuses to budge. A flat line is basically the universal symbol for an object at rest. To put that into perspective, let's ground this in a very specific example from our source material. Imagine a vehicle is parked exactly 40 meters away from its starting point, or the origin. Because it's not moving, its position stays at that exact 40-meter mark, second after second after second. So its graph is simply a straight horizontal line permanently situated right at the 40 on our vertical axis. But what happens when the driver finally turns the key and pulls out onto the open highway? Well, if the car sets the cruise control, let's say moving exactly 20 meters forward during every single 1-second interval, the graph changes completely. It becomes a straight, slanted line moving diagonally upward. This slanted straight line is the exact visual signature of constant velocity. It basically means the vehicle is covering equal amounts of ground in equal amounts of time. Nice, steady, and entirely predictable. Now for section 3, the curve of acceleration. Let's see how this builds.
Okay, so the driver gets a little impatient and decides to step firmly on the gas pedal. When you floor it, you aren't covering the exact same distance every second anymore. Every second that ticks by, you're moving faster and traveling farther than the second before. On our graph, this changes the game entirely. The line is no longer straight. It actually begins to bend and curve upwards. A curved line instantly tells us that the velocity is changing. The object is in accelerated motion.
Just think about this comparison for a second. On one side, you have the steady, straight, slanted line of cruise control. On the other, the dynamic, sweeping curve of acceleration. In the curved graph, the object might travel a pretty short distance between the 4 and 6 second mark, but by the time we hit the 10 to 12 second mark, it is covering a massive amount of ground in that exact same 2-second window. And this brilliantly illustrates how the mere shape of a line, straight versus curved, perfectly mirrors our physical reality. Which brings us to section 4, calculating your velocity. Being able to read the shape of the graph is awesome, but what if a police officer pulls our car over and wants to look at the exact data? Now, don't let the idea of mathematical equations intimidate you here. Calculating velocity from a graph really just comes down to one remarkably simple concept: looking closely at the steepness of the line. In math, we call this the slope. If you can measure how steep a straight line is, you can definitively calculate exactly how fast that object is traveling. We do this by breaking it down into 3 super easy steps. Step 1, you just pick 2 points on your line and find the change in position. So where did it end up minus where did it start? Step 2, find the change in time. How many seconds pass between those 2 points? And step 3, just divide that position change by the time change. That's literally it. Distance over time. As our source material elegantly states, the slope of a line is the steepness of the line. That steepness gives you the precise rate at which the vertical axis, position,
is changing relative to the horizontal axis, time. Let's actually run the numbers from the source real quick. At the 2-second mark, our car is at 40 meters. At the 4-second mark, it's at 80 meters. Step 1, 80 minus 40 gives us 40 meters of total travel. Step 2, 4 seconds minus 2 seconds means the trip took 2 seconds. Step 3, 40 meters divided by 2 seconds equals an exact velocity of 20 meters per second. So the absolutely crucial point here is that the math directly translates to the physical speed.
Now we are ready for Section 5. Who is moving faster?
We are taking everything we just learned and applying it to a real-world rivalry. 2 cars side by side on a highway, Object A and Object B. Instantly, our brains can process this comparison. Object A has a very gentle, lazy slope. Object B is angled much higher. It has a distinctly steeper slope. Without doing a single lick of math, you can tell exactly who is winning the race.
Because the slope for B is steeper, it means that for any given chunk of time you choose to measure, Object B is traveling a farther distance. It has a greater displacement. Therefore, as the source states, the velocity of B is higher. A steeper line always equals a faster speed. Well, we've successfully decoded the straight lines. We know flat means parked, slanted means steady speed, and steepness tells us exactly who is going faster. But as we wrap up this explainer, I want you to think outside the straight line box for a second. Let's return to that curving line of acceleration. We know a curve means changing speed. But here's something to really chew on. If the steepness is constantly changing at every single point on that curve, how do you calculate the exact velocity for one specific isolated split second? Our source notes that finding the velocity at any instant of a curve geometrically requires moving into higher grade math. It is the literal gateway to calculus. So the next time you push the gas pedal and feel yourself pushed back in your seat, ask yourself, how would you draw the math of that single fleeting moment?